Effect of thermal properties of storage material on packed bed performance. Abstract for concentrated solar power plants, packed bed of rock represents a good alternative to two-tank molten-salt thermal energy storage system. In this study, a two-phase numerical model is developed and successfully validated with experimental data. A parametric study was carried out to assess the effect of thermal properties of storage material on the thermal behavior and performance of rock bed energy storage system. The results obtained show that the thermal capacity and conductivity of storage material have a great effect on thermocline zone, thermal stratification, stored energy during charging, recovered energy during discharging, and on the efficiency of the storage system. Keywords: thermal storage, storage material, rock bed, thermal capacity, thermal conductivity. Introduction. The integration of thermal energy storage system, TES, in concentrated solar power plants, CSP, is a crucial necessity to overcome the inherent characteristics of solar energy. It is intermittent and stochastic. It is therefore essential to develop an efficient TES systems, which are less costly and eco-friendly. The packed bed of rock using rocks as storage material and air as heat transfer fluid HTF represents the most suitable TES system for the solar air heaters 1 to 2. It is environmentally friendly. It is based on the concept of direct storage in a single tank, which considerably reduces the overall cost compared to indirect two-tank molten salt storage system, and it is usable at high temperature, which optimizes its efficiency. In addition, heat transfer between HTF and storage material is direct, therefore, the use of the heat exchanger is eliminated. The thermal storage system works according to two modes, charging mode and discharging mode. During charging process, the hot air flows through the tank from the top to the bottom to heat the storage material. However, during discharging process, the flow direction is reversed. The cold air flows from the bottom to the top of the tank to recover the stored energy during the charging phase. The majority of studies on packed beds, especially air/rock bed TES systems in the literature, are focused on thermal charging process. While the thermal performance depends on the success of the two process, charge and discharge. In particular, Yang and Garimella carried out detailed studies to investigate the effect of the Reynolds number, tank height, and particle size on the discharge efficiency of a molten salt/rock bed TES system 3, 4. The aim of this work is to investigate the effect of the thermal properties of the storage material on the thermal behavior and performance of the rock bed TES system during the two process of charge and discharge. To this end, a transient two-phase model was developed and validated with experimental data taken from literature. 2. Modeling. For modeling the thermal behavior of air/rock bed, a two-phase model has been developed. The major advantage of this model is that it allows to describe the heat transfer in the fluid and solid phases separately, taking into account the heat exchange between the two phases. The main assumptions of the numerical model are the following. The air is treated as an ideal gas. The flow of fluid through the rock bed is laminar. The temperature distribution in each rock is uniform, by 1. The thermal properties of the fluid are temperature dependent. No internal heat generation. The heat transfer by radiation is neglected. The numerical model considers also the thermal losses. It is described by the following energy equations. For fluid phase. For solid phase. Where Tf and Ts, K, are respectively the fluid and solid temperature, Hf, W/m2K, is the convective heat transfer coefficient between the fluid and solid phases, A, m2/m3, is the surface area per unit volume, and E is the void fraction. The detailed description of the numerical modeling and the initial and boundary conditions is performed in our previous work 5. The numerical model was successfully validated against the two experimental data taken from the literature 6,7. The stored energy over the storage height is calculated by where A, m2, is the surface area. The efficiency of the storage system is defined as the ratio between the recovered energy during the discharging process and the input thermal energy during the charging process. G, kg/sm2, is the mass flow rate per unit cross-section. 3 results. A. Thermal capacity. The thermal capacity characterizes the amount of thermal energy stored in a material when the temperature rises. It is defined as the product of the specific heat, Cs, and the density, S. The choice of storage material is essentially based on this physical quantity, which must be high enough to optimize the thermal performance of the storage system. Oscar and ETAL8 have found that the thermal capacity of the storage material must be greater than 1 mJ/m3K. In addition, the large values of the thermal capacity leads to a decrease in the storage volume, which optimizes the efficiency by reducing the cost of the storage system and the thermal losses 9, 10. To characterize the influence of the thermal capacity of rocks on the performance of air/rock bed TES system, a comparative study of 3 different rocks, gabbro, quartzite, and sandstone, was carried out. The selection of these rocks was based on their thermal and thermomechanical properties. The main characteristics of the selected rocks are illustrated in Table I. To clearly show the effect of thermal capacity of storage material on the packed performance during the charge process, 4 hours of continuous charging has been simulated. Fig 1 illustrates the evolution of the average temperature of the 3 rock beds during the charging process. It shows that the average temperature in the sandstone bed increases rapidly than that obtained in the quartzite and gabbro beds. In addition, the axial temperature of the sandstone bed at the end of the charge is higher than that of the gabbro and quartzite beds, Fig 2. These results can be explained by the low thermal capacity of sandstone compared to quartzite and gabbro. During the thermal discharge process, the cold air enters from the bottom of the tank with a temperature equal to 293 K to restore the heat stored in the charging phase. Therefore, during the discharge, the temperature of the solid phase decreases with the time for the 3 rock beds, which can be seen in Fig 4. It shows also that at the end of the discharge, the temperature within the gabbro bed is higher than that obtained in the other beds. This result can be explained by the high value of the energy stored in the gabbro bed during charging in comparison with the quartzite and sandstone beds. The outlet temperature of the fluid during the discharge process is the most important criterion for evaluating the performance of thermal storage in the rock bed. This temperature is used to assess the degree of success of discharge process. In fact, the thermal capacity of storage material has a significant influence on this parameter. Fig 5 shows that the fluid outlet temperature during the discharge phase decreases as a function of time for the 3 rock beds. Also, it is higher for the gabbro bed compared to the quartzite and sandstone beds. In addition, the thermal capacity of the storage material influences the efficiency of the tank. Fig 6 shows that the efficiency of the gabbro bed is greater than that of the quartzite and sandstone beds. Summarizing, a high thermal capacity of storage material optimizes the performance of the air/rock bed TES system. B. Thermal conductivity. Thermal conductivity is also an important parameter that must be taken into account when choosing the storage material. In general, the thermal conductivities of natural rocks varies between 0.2 and 10 W/mK at ambient temperature 12, 13. Usually, natural rocks with high quartz content have higher thermal conductivities. 11. The thermal conductivity of the storage material influences directly on the heat diffusion in the rock bed, which also influences on the thickness of the thermocline zone during the charging and discharging process. To highlight the effect of this parameter on the performance of the tank, two storage materials with very close thermal capacities and very different thermal conductivities were chosen, aluminum and gabbro. The thermal conductivity at ambient temperature for aluminum and gabbro are respectively 204 W/Mk14 and 2.19 W/Mk. The solid temperature profiles within the aluminum and gabbro beds after 1200s and 4800s of the charge are plotted in Fig 7. It shows that the thermocline zone formed in the aluminum bed is wider than that in gabbro bed. Also, the temperature at the top of the gabbro bed is higher and very close to the air inlet temperature, while the temperature at the bottom of the aluminum bed is higher compared to the gabbro bed. As a result, the aluminum bed stores more energy at the bottom. However, in the gabbro bed the energy stored at the top is much higher, which has a positive influence on the performance of the storage system. The fluid temperature at the outlet during charging is defined as the minimum temperature reached by the fluid after heating the storage materials. During the charging process, the temperature of the fluid leaving the gabbro bed remains close to the minimum temperature of the tank, 293 K. Whereas, for the aluminum bed, it increases rapidly with the charging time, Fig. 8. The result of Figure 8 influences directly on the heat flux evacuated during charging, which corresponds to the heat flux at the exit of the tank. Fig 9 shows that the heat flux evacuated increases rapidly for the aluminum bed as a function of charging time. However, for the gabbro bed, it is equivalent to its minimum value and it remains almost constant during the charging period. This result means that the aluminum bed has not absorbed the majority of the heat supplied by air like the gabbro bed. The temperature profiles of aluminum and gabbro beds during the discharge process are illustrated in Fig 10. As can be seen, the variation of the solid temperature in the aluminum bed is smaller in comparison with the gabbro bed. The thermocline zone formed within the aluminum bed is wider than that formed in the gabbro bed. Therefore, using the storage material with high thermal conductivities induces a reduction of the degree of thermal stratification in the storage bed. The thermal conductivity of the storage material also influences the temperature of the fluid at the exit during the discharge process. Fig 11 shows that the outlet fluid temperature during the discharge for the aluminum bed is higher compared to the gabbro bed. Fig 12 shows the evolution in time of the efficiency of the two storage beds. As can be seen, the efficiency of the gabbro bed is more important compared to aluminum bed. Therefore, using the storage material with high thermal conductivity decreases the efficiency of the storage system. To conclude, the thermal conductivity of the storage material significantly influences the thermal performance of the storage system. The results obtained showed that the stored energy, the outlet fluid temperature during discharge and the efficiency of the storage system strongly decreases with high thermal conductivity values. For conclusion, the two-phase heat transfer model was developed allows to study the thermal storage in packed bed of rock test system during the charging and discharging process. The numerical model was successfully validated against the experimental data taken from the literature. A detailed study was carried out to investigate the effect of the thermal properties of storage material. The main results obtained in this work are: the natural rocks have shown that they are the most suitable storage material for thermal storage in packed bed using air as HTF. The thermal capacity of the rocks must be high enough to optimize the performance of the TES system and to reduce the storage volume. The thermal conductivity of the storage material have a great effect on the performance of the packed bed TES system. The use of storage materials with low thermal conductivity limits the diffusion of heat in the bed, which influences the degree of thermal stratification and the thickness of the thermocline zone. According to this study and those of Tascaden et al. 2017-11, gabbro rock presents the most suitable thermal storage material for air/rock bed TES systems.